Hello everyone, my name is Griffin Kindred and this is my EAS high-speed aerodynamics project 1. Okay, so for the project I kind of pretty much followed the video. I played around by trying to make my own wind tunnels, but I couldn't get the shock, so for the sake of simplicity I'm just gonna do what the video did. So the first thing you have to do, or the first thing I did was excuse me, I needed to import the points as well as the lines. So for that, the first thing I have to do is get the points. As we can see, as we generate, you can see we have a nice little wind tunnel point. And now the next thing we need to do is 3D curve. Nozzle lines, generate, and there we go. Now the next thing is we need to make a few points. Okay, so now we have our curve and our lines that connect everything. So once we do that, we need to make our surface. So for that, we're just gonna surface from edges. We're gonna select everything, the whole outline, apply, generate, and there we go. A big thing that we need to do so we don't cause any problems is we need to suppress the line body. I was having some trouble trying to figure out why I was getting errors, but make sure you suppress that. Okay, so now it is time to mesh. Alright, so here we have our mesh. All we need to do really is get some geometry. Let's select our body, and then we whoops, let me try that again. Let me import method. There it is, and I like to use the triangles method. And then once we do that, I'm going to make my element size 0.0025 meters. I found that's the best sort of medium point for me, so we're going to let that go. And as you can see, we have a nice mesh with triangles. One of the nicest options to do also is inflation. Now I've did it with a little bit of the other wind tunnels I was trying to make. It's really good for getting really precise meshes along the walls, which is great for the wind tunnels. But for like the video that I was watching, it really wasn't necessary. So I just stuck with the video. So now that we have our mesh made, I need to make my name sections. So I'm going to get the edge tool. Let's name this inlet. This is outlet. Also, I'm pressing N. It's faster than having to go through all the different keys. And there we go. So now we're just going to update. And that's it for the mesh. Now for the setup. Double precision. Something I learned from the TA is you can add more than one core processor. Makes things go a lot faster. Okay, for the setup. Pretty much up until this point, for both part A or part 1 and part 2, everything is going to be the same. So for part 1, where it's isentropic flow through the entire tunnel, we need to make this density based. We're going to make sure the energy equation is on. It specifically said in the handout that this is inviscid. So that's what we're going to do, is make sure that's on. We cannot have our air be a constant. We need it to be an ideal gas for this to work. And then another thing we should do is go to operating systems, and since this is try to be as realistic as possible, we want everything 0. Make sure gravity's on. Density, temperature, pressure is all 0. Just something the TA recommends. And now for the inlet, we're making this a pressure inlet. And for our pressure, we need to make this, well, I made it to, this will change varying on what you do. It doesn't have to be exactly like this, but this is what the video did. And after trying many hours to get something, I'm just going to follow the video. So there we go. Oh, whoops, sorry, I didn't mean to do that. So for the supersonic, it should be just really close to your gauge. It doesn't really matter from what I've looked up. The temperature from theoretical values should be 308 Kelvin. Let's apply that. And then for the outlet, we just need to make this super low. Since this is isentropic, we're going to make it 33.7 kilopascals, or this number be exact. We want to make that static pressure because that is what we're using. And then the temperature will also be a little lower. So we apply, so we have our energy, inviscid, ideal gas, we have our operating conditions. We made sure that it was on density based, and I think we're good. Oh, sorry. We need to make sure that our residuals, for better, more precise measurements, making this 1e to the 6. I'm going to add this for everything. Okay. And then for initialization, we want to make this standard, compute from the inlet, initialize. Now, from what the TA was saying, you can add more or less initialization or iterations. You ideally want your number, if you do it another way, you want your numbers to be about e to the negative 14. So just a word of advice. And then once this is done, we're ready to go to calculate. Okay, so I just do 5,000 for iterations. This is what the TA was recommending, so I'm going to do that. It converges at about half of 5,000, so just having it at 5,000 makes sure that I don't have any problems with it converging. So I'm going to calculate. I'm going to pause, and then I will come back as soon as it's done. Alright, so we are back. It has converged, as you can see. It took 2949 iterations, but we're here. So now what we need to do is we need to get our contours. It's very simple. We just go down to the graphics tab, and as you can see, I'm just going to go through them all quickly. We have our pressure contour over there. So we got pressure, temperature, density, velocity, which actually I was told the x velocity is probably better for what we're doing, even though it really doesn't make a difference from velocity magnitude, but for our sake it's what we want. Speed of sound, oh whoops, not specific heat, my bad. Speed of sound, and then Mach number, which as you can see, around kind of the bluish green is where it starts to change. That's where Mach of 1 is, and we see that it is good with our wind tunnel simulation. Right where Mach of 1 is right where the throw is, so the results look good. Now, to find the XY plots of a center line, we're going to need to go to results. We need to create a line. So basically how this works is these coordinates are based on where this is relative to the origin that we made into the geometry. So this wind tunnel was made with the y-axis on the very left. So the x0 is going to be 0. X1 is going to be, from what I have, 0.8401 meters. And the y's are 0 because it doesn't go up or down. Okay, so just to make sure that our center line is good, we can display it like so. And as you see, the yellow line is our center line. It looks good. So now what we need to do is we can find our XY plots. So all we have to do is just select our line, select what we want, and we save the plot. So as you can see, we have the pressure, density, velocity, Mach number, temperature, speed of sound. And I think that was all. Sorry, x velocity. So there we go. There is one other thing. I know this is half. I know that we only see half of the wind tunnel, but if you want to see the entire wind tunnel, there is a way to do it. You can go to results. You're going to get the same thing from what I just did, even though it's only half. It's still fluid, still makes it good. But just for the sake of the video, to show how to find it with all of the to make the full wind tunnel, we can just go to the results tab. I think that is the results tab. Yes. And we're going to need to wait for it to load. There we go. It's very simple. We select our symmetry 1, surface body. We want to apply a reflection from the ZX. And as you can see, we have our beautiful wind tunnel now in full form. And now we go back to symmetry 1. Here's our variables. Let's say we want to see what pressure looks like. There's our pressure gradient, our contour. We have temperature. We can get velocity. So there's what all of those look like. So I'm going to pause, and when I come back, I will go over part 2, which is the shock of the wind tunnel. Yep. All right, so I am back, and now I will be going over part 2. That's right, I will be going over part 2, which is the 2D simulation of a shock in a CD nozzle in Fluent. Now, pretty much everything up to the setup is going to be the exact same. That's why I'm just going to make it in one video. The geometry is the exact same, where I imported the lines and points. The mesh will be the same, just the triangles with my 0.0025 meter element size. It's going to be the exact same. Now, all the way up to setup. Now, as far as the setup, we have density based. It's going to be density based. We have the energy equation on. We have inviscid. It's going to be inviscid. And then everything again, the air is ideal gas. The boundary conditions, the operating conditions, we have 0 gravity, 0 temperature, 0 density. Now the big change is now the inlet. The inlet will be the same. We still have our 238,828 kilopascal inlet with a small supersonic, or a little lower supersonic. The thermal temperature will stay the same. The big change is now, instead of the small, I think I had around 38 kilopascal, to get the shock, we now have 160,000 Pascal. And then, so we make sure that's static. I went ahead and already did all the iterations. So from there, make sure our residuals are 1e to the 6 so we can get more precise. As you can see on the right, I've already gone through the iterations, but just to show how I do everything again, we would go to inlet, we initialize with standard initialization, and then once we do that, I calculated with 5,000 iterations. As you can see, there is a lot of oscillation going on, which is good. So now that I have that, I'm going to show all the contours just to show that we did get a shock. So if we go to pressure, static pressure, as you can see, we have a clear shock right here on the right. So we go through density. Looks pretty similar. Velocity. Let's do velocity in the x direction. And then we have our Mach number. We have our temperature. And then we have our speed of sound, or sound speed as it's in Fluent. So there's all the contours. As you can see, clear line, clear halt of everything. So the XY plots will look very different than the isentropic flow ones. Again, all this, I'm just going through this quick because it's all going to be on the Project 1 file, or the PDF as well. So the XY plot, just to go over how I made the center line, I go to create line rate, and then I go to 0, and then the end of my wind tunnel, which is 0.8401. That's right. That's how far away it is from the origin of the geometry. And then, as you can see, if we go through the XY plots, we can see static pressure. Let me go through the center line. As you can see, we obviously see a huge increase as it was going down. We have an increase there. We go to density, we see a huge bump up. Velocity, huge bump. X velocity, same, almost the same thing. Mach number, huge bump down. Temperature goes up. And lastly, the speed of sound, which we should see it go down and then a huge bump up. So that is that. And then lastly, I just want to show that I know I made half of the wind tunnel, which is fine. Fluent does a good job with making it simulate as the whole. And then if you wanted to make it reflected to have a nice full wind tunnel shock, all you have to do is just go to your surface body, your apply reflection, the ZX plane, and then apply, and there you get your reflected surface. And then you can go to your symmetry 1, you can go to variable, you can find your velocity, you can find your density here if you wanted. Everything was just on the results and it was just faster, so that's what I stuck with. We can see temperature, we can see pressure. I don't know if I already went through that. So yeah, so we have all those, and that is pretty much it for the Project 1. So I think whoever is listening, I thank you for listening. And yes, I did this at 4 a.m. Thank you very much.